All right, then. This is my second time filming this. But anyway, for this type of poem challenge, or for the new type of poem challenge, I'm gonna be doing like some slideshow to, I guess, to tell you guys what's the method of solving this, or like what was the point of this challenge, and like, yeah, if you guys like this idea, or maybe I'm just gonna keep on doing this just so I could learn new stuff. Either way, let's get started. So with this challenge, the challenge that we're gonna be doing today is a poem challenge by Hack the Box called Blacksmith, which is, yeah, a poem challenge released a couple years ago, and it's part of the Intro to Binary Exploitation course, or path in Hack the Box. So anyway, let's get started. So the point of this challenge was to understand uh, CComp. So what's CComp? I have it right here. So CComp is a system call in the Linux kernel which restricts what other system calls the user can execute. So what does this mean? So let's go on to the next slide. So in this case, we have C code. I stole this C code from Pone College. So I'll let you guys. I'll walk you guys through it. So it sets up a ccomp filter.ctx, and then after that, it allows for all type of system calls. And after that, we add a rule, and this rule kills any system calls that do exec. So execution. I think that's what it stands for. Execution. System calls gets killed, and after that, it's loaded into the rule set. After rules add, and then you just you load that rule inside the rule set. And then right here we have an example of a execution system call being placed, and we'll see what happens. So in this case, the guy from Pone College, he just printed out right here. He catted out the program to make you guys sure see what the program is running, or what the program is gonna execute. And after that, he executes the program, and you see bad system call. So it restricted. It allowed all other system calls except this exe one, and that's why I said bad system call. That's basically ccomp. And how we gonna do this in this challenge? So with this challenge, we're gonna be using ccomp tool. So what's ccomp tool? So it's a project that targets, but it's not limited to CTF, ccomp sandboxes. So this tool allows us to analyze ccomp rules, because overall it's pretty difficult, and you'll see why it's difficult. Or maybe it's not that, but like for a new person trying to learn them, it's pretty difficult. So anyway, let's get started with the challenge. So uh yeah, let's go right here. So I guess for usual, I'll just check the file, and then I'll just do a Blacksmith to check what it is. So it's a 64-bit file, and it's not stripped. So that means the original names of the file are still there. They should still be there. So anyway, we want to do a check. I already have my Python script already ready for checking the file permissions. So we do bat check.py. This is what I use. So I do Python 3 check.py. We see full real raw canary found. Seems to be a canary. NX is disabled, so that means we could run shellcode. So that's where we get the idea. We could run shellcode, but I guess we're limited on what we could do because of the ccomp that it's enabled on this file, and we're about to see where. And then we have pi enable and RWX segments. So anyway, rewrite execute, I think, segments. So anyway, yeah, let's run the program real quick to see, have an idea what it does. So we'll just run Blacksmith. So we got 1 and 2. So we press 2, exits out. Okay. Press 1. We're giving 3 options. So we'll press 1 again. We get bad system call. Gives us an idea. We'll go with 1 again. Press 2. Or we could type something. So I'll just type hello world. Segmentation fault. Another thing to keep in mind. Blacksmith 1, 3. And then bad system call. Okay. We have a general idea what we think the binary does. But we could now look at Ghidra. So if we look at Ghidra, and this this is gonna give you a preview of what it does. So anyway, so we see the strings right here. So it says right here, if you enter that something that's not 1, we will exit out right away. So that's why if we enter 2, we exit it out right away, because it's not something that's 1. So other than that, if we enter 1, we see that seek gets called, and if we click seek, we see the ccomp rule. See, look, it matches very closely to what we had beforehand. So if we go right here, it matches it very closely to our ccomp rules. See, look, so certain rules are added, but we're not sure what these rules does, because look at this, it has like this weird hex value, but we'll check it later on. Or maybe if you've done a lot of CTF, this looks familiar, but for me it doesn't. So anyway, these ccomp rules are being placed, and then after that, the first thing that pops up is 2. So if we check 2, let's see. So we check to shield. We see that code is being executed for the most part. So code. So we see all of this, but right here the read in part. So it reads in this part and then it executes whatever. So that's why we're getting seg faults. So I'm guessing we're supposed to write shellcode that's supposed to be able to execute with this. So now let's check on more. Let's check on it just to be sure. Well, let's see. We have bow. What is bow? So let's see. We have bow. This bow is range. This bow is range too bad. Oh, nothing that bad. Main. If equals 2, else if it equals 3, else we do right and then exits. Pretty weird, but anyway, yeah. So the whole point of it is to notice that in shield we could run code right here in this part, but we're limited to what kind of code we could run because we have these ccomp rules. So we want to be able to know what these ccomp rules are for the most part, and that's where ccomp tools comes into play. So if we go right here on ccomp tools, I think I have it right here. So what we'll do is do ccomp tools, and then we'll dump the ccomp rules from this binary. So anyway, so we do this. We're giving 1 and 2, so we know 2 exits out the program, and we want to be able to reach to the point where it executes code. So for now we'll press 1. And then the option that it allows us to execute shellcode is option number 2. So we press number 2. We're going to see the ccomp rules that allows. So if you see right here, it says return allow and return kill. So if we start from right here, if it doesn't equal to x86-64, it goes to 010, which is kill. And right here, if it's it goes to 005, which is this. If it goes to 0010, which is this, exits. Okay, then. But let's check right here. So if A is equal to read, it goes to 009, which is right here, 009, which is allow. So we could assume that everything that says go to 009 is allowed. So we're allowed to read, write, and open. So keep that in mind. We're allowed to read, write, and open. Those are the only things we're allowed to do. Now, if we go back, to our thing right here, it says that our little description says you're the one who is capable of saving this town and bringing peace upon this land. You found a blacksmith who could create the most powerful weapon in the world. You can find him under the label flag.txt. So it gives us the name of the file. So I'm guessing for the most part, or like the whole point of this challenge is to open the flag, read the flag, and write the flag. To write shellcode that opens the flag, reads the flag, and writes to the flag. That's basically the whole point of the challenge. And what you could do technically is like go on GoBot and just copy and paste like all this and send this as like a send line and send all this assembly code. But what we're gonna do, which is like the shortcut version of it, is basically use advantage of Pwn Tools functionality. So let's get started. So I already have my script already made, so I'll do backcat solve.py, and we see right here. So right here we have from Pwn import all, and then right here we get the name of our executable file, and then we pass it on to context.binary, and then we run the file. So that's basically what this does. And now right here I have printing out the the assembly code being written out. This is just for me. This is for my sake. But what this is basically doing, it's opening flag.txt. This is the code that opens flag.txt. And then what it's gonna do after, it's gonna read in 3, which 3 stands for file. So we're reading in a file, and RSP is the location of the flag.txt. And I'll go over that with you guys. And then we have OX100, so we want to be able to read in 100 bytes. And then later on our payload we have write, which 1 stands for standard out. So it's gonna print out the flag.txt, which is located in RSP, and it's gonna print out 100 bytes. And then after that, I have it right here printing out my payload. And then we have 1, 2, and then right here we send our payload, and then we receive it. So if I run this locally, let's see, we have flag. Yeah, we have our fake flag. So if I run this locally, we'll see what it does. So Python 3 solve.py. So we see right here. So we see this is our flag.txt but in hexadecimals, and it's getting passed to RAX, and then it pushes RAX, so that means it's gonna be the top of the stack, and the top of the stack is located in stack pointer, and the stack pointer is gonna go to RDI. And if you guys don't know what RDI is basically, if I remember correctly, RDI just holds the. Oh, we're just waiting for this. Oh, see, look, we are printing out fake flag. So I printed out our flag. That's locally, but anyway, let's go check right here. Uh, RDI and system calls. I'm pretty sure it's the RDI. Talking to us with syscalls. RDI. See, used to passing the first argument to a function. That's what we're passing in. And the first, and then if we go right here, it's open. Open system call. And then open system call. The very first thing that we want to pass in is the path. And the path, is the path. So that's going to be our flag.txt file, basically. So that's where RDI is being saved at. So anyway, let's go through this. So it opens it, and now we want to read in. So 3 signifies for we want to read in a file. And then RSP is going to hold flag.txt. And you see right here, RSP currently holds our RDI value. RSP holds our flag.txt, and then zors out EDX, zors out EDI, and then right here, it pops RAX, which is something that we pushed in, and then after that, it does the system call. Now, after that, it reads in 100 bytes. We want to be able to read in 100 bytes. That's why this is so long. No, this is for writing out. Never mind. And after that, we want to write. This writes out to standard output, which we could see right here. And then our RSP is going to hold our flag.txt. And then after that, it writes out the constants of 100. So if we go right here, I could even change this to like something even smaller. So to make you guys understand. So nano solve.py. We could even change this to like, 10? To see it, you're going to see the output be even smaller. Python 3 solve.py. We're going to wait on this. Fake flag, and see, look, you know how the output got smaller? So what is Python 3 OX10? I don't even know what that is. 16. So it printed out 16 bytes. Yeah. Now, what we could do is probably like even inspect more of this. We have time. Yeah, we have time. We have plenty of time. Clear ls nano solve.py. What we could do is just probably print out everything. Okay. What we could do is just copy this. And then we just do payload 2. We'll call this payload 2, but we'll just delete out the ASM. And we're about to see this entire thing into play. And then we'll just do this. Yeah, that's good. Shellcraft. We'll do payload 2, 2, 2, and then print payload 2. And while we're at it, we'll just connect it to our remote host and get our flag and turn it in. So just delete that, and then payload. That should work. We should see our payload 2. Yeah, this should work, hopefully. Yes. Oh wait, let me remove this last part, this payload right here. Now this should work, and then hopefully I should have my thing up. Let's do this. Oh wait, do this again, and then we want to get this Hopefully it's still. So we'll do Python 3 solve.py, and then it's gonna print out our things right here. And then we get, oh, we probably need to make it a little bit more bigger. So nano solve.py, and then we want to make this a bit more bigger, probably like 20, OX20. And then we see our entire, I guess, assembly code right here. And we just wait for this. And we get right here. So we get our flag. So that was basically about it for this challenge. I guess learning how to use CCOM tools, and then just, I guess you could write your own assembly code, but also, like, I guess for the most part, you could probably take advantage and use hack the box, no, not hack the box, Pwn tools, the Pwn tools functionality to make your life a lot easier. But let's see right here. So call read, system call. Oh, this is that. Just call read. Zor EAX absorbs it out, so that's probably 0. It pushes 3. Pop RDI. Zor EDX. RSP gets moved to RSI. So write, and then buff is gonna equal to RSP. The stack pointer. You push 3. You pop RDI. It goes to RDI, and RSI. Stack pointer gets moved to RSI. What's I think RSI register. Used to pass in the second argument. So yeah, so RSP still gets passed. So the RSP, the stack pointer, gets pushed to RSI right here. This is just a move, so nothing happens here. You pop RDI, so whatever values in RDI, it pops out. So it makes sense. And then pushes 3. Pop it. Oh, because RDI hold it RSP. Oh, that kind of makes sense. So, okay. And then after that, move RSP, which is a stack pointer, to RSI, which is also the second value, which is the right value right here. So yeah. Anyway, pretty cool stuff for the most part. Yep, pretty cool stuff. Anyway, that was about it for this video. Hopefully you guys learned something new, and hopefully you guys liked the new style. Hopefully I explained it well enough. Anyway, that was about it for me, and later. Peace.